Okay, welcome back. This is the last video I think I'll be recording for this year. And I just wanted to wrap up a few more thoughts about color because I actually was noticing as I was going over the test that there was a concept or two that I didn't cover. And I thought, well, best to cover it now. So if you remember when we last talked about color, we were talking about ambient color and the fact that local color is purely an illusion and that artists became more and more interested over time, really examining how much color is in the color of light and how affected by light and atmosphere and reflected color real color is, so that all real color is ambient color. And that led to finally talking about these paintings by Monet. But when we got to these with all of this color, I thought it was important for us to really understand exactly what is the shape and nature of the color wheel. Which leads to this diagram. When we're in school, we learn that the color wheel is round, circular, and that's a bit of a lie, but the bigger lie is that the color wheel is evenly spaced, that you have three primary colors and that the spacing between them is equidistant, like the distance from red to yellow and yellow to blue is equally the same, and that then the distances between or the halfway points are equally distant, right? Similar. That the halfway between yellow and red is the same distance between the two of them as the halfway distance between blue and yellow. And that's a nice fiction, but it isn't really completely accurate. This is a chromaticity chart, which, I mean, number one, keep in mind, is based off of projected light, so it's much more based off of an additive system rather than a subtractive system. But nonetheless, it describes the actual structure of the wavelengths of light more accurately. And one of the things that you notice is that the traditional primaries are far less important than you would think, because if we only stuck with the traditional primaries, like yellow would be right there, right, and red right there, and blue right there, that's a very narrow triangle of the color wheel, and it pretty much ignores most of the upper part of the color wheel. And when you look at the chromaticity chart, it also starts to make clear that there are certain things that don't make sense in a normal color wheel that start to make sense here, such as the fact that there is so much more room in the greens, right? If you were to just sit in a quiet room and imagine all the different possible greens, you would quickly realize that there's way more variety in the color green than there is in, let's say, the color orange. And the chromaticity chart proves that to be quite accurate. Another thing you might notice about it is the immediate drop off right there. This is the point where the spectrum goes outside of being visible by human eye. Okay, so that's point one, just to get you to understand that the structure of color is more complex, but then that also raises another point. Earlier, when the first unit on color, we talked about value, hue, and intensity. And a lot of thinkers about color, and keep in mind that the Munsell spheroid here actually is much earlier as a model. Let's go back one. It's much earlier than the chromaticity chart. But what this is based on is the idea that if you really start thinking about those three components, right? Value, I was about to point to the screen with my finger. Value, go back again. Value being the center axis, right? Going up and down. Everything that's up and down, everything that's down goes towards dark, right? Everything that's up goes towards light. Intensity being how far away from the center axis you are, right? The further away to the outside, the more intense you get. The closer to the center axis you get, the more neutral you get. And then spectrum or hue change is based on how you go around, right? So it's the circularness. And originally people thought that the color, when they started realizing that there are three dimensions to color, that those should map out in a model like a sphere. But Munsell started to figure out that they don't map out like a sphere at all. The reason is, and you can see it very clearly here, is that every hue is most intense at a different value level. right? To give you like to imagine, try to imagine this yellow-orange. Try to imagine it at its most intense form, right? And then what value it is. And then try to imagine a really dark but really intense version of that color. And you probably start to realize you can't, because that does not exist. There is no really dark, really intense version of that yellow-orange. But at the same time, if we're looking at this blue on the cerulean side here, um, and you're trying to imagine, well, when is it the most intense? Notice it's much more intense at a mid value, right? And doesn't lose a lot of intensity even as it gets darker, at least not until about here, right? Like even this value right there is pretty intense, but it does lose quite a bit of value as it gets lighter. And you would find that if we were looking at a blue-violet or a true violet, the shape would even be further down here. It would be most intense at a much darker value level. So because of that, the model of color is lopsided. It is this misshapen form, which we call a spheroid, rather than a perfect sphere. So, and actually, just to go back, that is the one, the Munsell color spheroid is a question on the test. I think it's one of the matching maybe. So make sure to pay attention to it. Okay, so the only other thing I wanted to talk about before I wrap this all up is color relativity. The basic concept that color perception, like all perception, is seen relatively. These paintings, Homage to Square by Joseph Albers, demonstrate it to a degree, in that as you're looking at it, a good example would be right here. Your eye can't help but look at this color, even though this is the same color from top to bottom, but to see it differently as we see this edge against that color versus as we see this edge against that color. We start to see it being lighter and cooler here, and then a little bit darker there. Here's a little chart that kind of shows you how these kind of things can work. In that this color right there is the same color as that color, which is also the same color as that color, or that color, right? And this color here is the same color as that color. And that it's just showing you that, like, you taking similar colors and putting them in different contexts, you can change the perception so that we can make a color look darker and cooler by pairing it with light and warm colors. Or you can make a color look cooler but also less intense by pairing it with warm and very intense colors. Whereas you can make it warmer, look more like a yellow, have more of a yellowish hue by pairing it with really dark and cool colors. We don't have a lot of time to talk about optical mixing, but I did want to cover the topic just very slightly. This has been of interest to artists since about the 1880s, 1870s. And Seurat obviously was one of the artists who was most obsessed with this idea of how to create color not through mixing it on his palette, but create mixing through in our eye. Like, and you may think, well, it looks like a silly idea to do in a painting, but when you think about it, this is the basis of all color printing, and this is the basis of all screens. Every screen, every computer screen, TV screen you're looking at is made out of optical mixing. But he didn't necessarily have all the science on his hands to know how to do this, like with a CMYK system, and probably didn't have a tiny enough brush for the dots to be small enough. Here in these, op art paintings, you can also see a different kind of optical mixing and different kind of illusions, where there's really only the one base color here, right? We start to think of this square here as a different color, and we start to think of this as a different color, but really the only thing that's changing are the bars over the top of it, and it creates the impression of all these different colors going on in the painting. Or even more effectively, we can see it in these two paintings, especially the Arthur Honer painting, where he's using a very idiosyncratic system, like to create this yellow. it's hard to see here, but like that perception of yellow right there is created by combining a yellow green and a pink, um, and or like a kind of an orangish pink. There is no actual yellow at all in that whole section that exists purely just in our eye. I can't remember. Oh, I guess that was the last slide. All right, well, that's it for color, and thank you very much. And hopefully you'll manage to watch this before taking the test tomorrow.